In this video, we're going to be going over percent yield, which is part of our learning objective for calculating the percent yield of a chemical reaction. So what do we mean by yield? Well, in order for reactants to turn into products, they need to collide with each other in just the right orientation with enough energy. Not all reactions actually go all the way to products. Sometimes there's a little bit of reactants left over. It could happen for a variety of reasons. Maybe they were just too far apart from one another to find each other. Maybe they reacted to form something else. Maybe they didn't have enough energy to form products. So there's a lot of different reasons why reactants might not go all the way to, why the reactants might not go all the way to products. But all these calculations we've been doing so far with calculating how much product can we make from a reaction, that's kind of a prediction of how much we could make, the most we could make. That's the theoretical yield. The theoretical yield is what we've calculated from our stoichiometry calculations. The theoretical yield is always calculated. It's a prediction of how much we could make if everything happened absolutely perfectly. But then there's the actual yield. The actual yield is how much did we actually make. So if we go into a lab and we do an experiment, we take how much product we have and we purify it and weigh it, how much do we have? And so the actual yield is always experimentally determined. It's measured. The percent yield is a ratio turned into a percentage of the actual yield over the theoretical yield. Since the theoretical yield is the most we absolutely could make, the actual yield should always be smaller than the theoretical yield. And that means that the absolute most we could make is 100%. But since the actual yield should be smaller than the theoretical yield, most of the time we end up with less than 100%. It should never be more than 100%. 100% is the cap on this. Percent yields are kind of like letter grade calculations, like 90% is really good, B's are good, 80%, and then 50% is not so great. And so like we want to optimize our reaction conditions in order to maximize our percent yield and get the highest percent yield we possibly can in the right conditions. And if we know our percent yield from doing different trials, we can use that to do some backwards calculations to figure out how much should we start with in order to produce the amount that we actually want. So here's a practice problem for you to see how much you understood from that. It reads, Sylvia calculates she should get 5.854 grams of a product. After she filters her precipitate, washes it, and dries it, and records the mass, she has 4.983 grams of product. What is her actual yield? Go ahead and pause the video and think about this. Unpause the video when you're ready to check your work. Well, this is really more of a vocabulary question than anything else. And so it's saying her actual yield. So this is how much does she actually have? She has this much. That is her actual yield right here. This is her theoretical yield. And this is her actual yield. So we didn't actually need to calculate anything. It told us the answer right in the problem. All right, here's an example of how to calculate the percent yield. In an earlier video on limiting reactants, we talked about the thermite reaction, which produces liquid iron. And so we calculated from that limiting reactant that we could make 195 grams of iron. Now we know that this is the theoretical yield. Based on those masses. This is the mass of a product. And so this is our actual yield. So to calculate our percent yield, we have to do 173 grams divided by 195 grams, and then turn that into a percentage. The grams will cancel, and so that's 173 divided by 195. And that gives us a decimal. Then we have to turn that into a percentage by multiplying by 100. And so that is equal to 88.7%. I needed 3 sig figs. Here's a practice problem for you. It says, without proper ventilation, the reaction of carbon and oxygen produces carbon monoxide. What is the percent yield if 40 grams of carbon monoxide is produced when 67 grams of carbon reacts with 30 grams of oxygen? Go ahead and pause the video and try to work that out on your own, and then unpause the video when you are ready to check your work. Okay, so the balanced chemical equation is up here, and so if we're given this, that's the amount of a product, and so that's my actual yield. That means I'm going to have to calculate my theoretical yield. I'm given 67.0 grams of carbon and 30 grams of oxygen. Since I'm given the masses of two different reactants, I have to figure out which one is limiting. That way I can calculate my mass of product based on the limiting reactant. So let's go over this. Let's see. If I use up all 67 grams of my carbon, then that is going to be how much carbon monoxide? It's 12.0011 moles of carbon. And then from my balanced chemical equation, I'll use up 2 moles of carbon when I produce 2 moles of carbon monoxide. Since it's asking for masses, I might as well calculate all the way to a mass. And the molar mass of carbon monoxide is 15.9. That is going to be 28.01. Alright, now let me get the setup going for the oxygen. So that's going to be 30.0 grams of O2, and that's 1 mole of C. And so it's 1 mole of O2. O2 has 2 atoms of oxygen, so we got to remember that its molar mass is 31.998 grams, not 15.999. Now I can cancel out my moles of O2 to get into moles of carbon monoxide, and then we'll cancel out my moles of carbon monoxide using the molar mass as above. Okay, so I got my setups. Let's see, 67 times 1 divided by 12.011 times 2 divided by 2 times 28.01. And so that's going to be 156.24 grams of carbon monoxide. 2459. Okay, get some extra digits just in case. So that's 30 divided by 31.998 times 2 times 28.01. And so that's 52.522 grams. So this is definitely smaller. And so this is going to be my theoretical yield. That tells me that my O2 is limiting. My O2 is going to run out first, and I'm going to make that much carbon monoxide. I'm asked to find the percent yield, so the percent yield will be equal to my actual yield of 40.0 grams of carbon monoxide over my theoretical yield. And then I'm going to have to turn that into a percentage. So 40 divided by my previous answer times 100 is equal to 76.158%. I'm going to need 3 significant figures, and so that will round to 76.2%. Here's another example problem where we are going to be taking our percent yield and then backwards calculating how much reactant we would need to start with. This one reads, from your previous trials, the reaction below gets 78% yield. If you use excess sodium sulfate, so this one is an excess, how much iron 3 phosphate would you need in order to produce 10 grams of iron 3 sulfate? So we need this to be the actual yield. And so this tells us that we will make 78 grams for every 100 grams we start out to make. So if we have our 10.00 grams, we're going to have to cancel out our actual yield and get into our theoretical yield. So that's our percent yield as a conversion factor. Okay, so that would tell us our target theoretical yield for the iron 3 sulfate. Then I would need to cancel out the grams of iron 3 sulfate. Got my subscripts backwards. I need to get into moles. Whenever we do stoichiometry, we always try to get into moles. And that would be moles of the iron 3 sulfate. Then I would need to switch compounds. So we got into moles. Now we got to switch compounds, and so that's my moles of iron 3 sulfate. The balanced equation, which has a 1 coefficient, and that's going to do 2 moles of FePO4. And now we're going to need to get out of moles. So our third step is to get out of moles. So for that, we're going to use the molar mass of iron 3 phosphate. So we'll cancel our moles of iron phosphate, and you get into grams of iron phosphate. And then we'll have our answer. I just have to calculate these 2 molar masses. Hold on. Okay, so I have calculated the molar masses and inputted them. So now I just need to type this into my calculator. And then I'll do divided by 399.86 times 2 times 150.816. And so that would be equal to 9.6710 grams. And then I would need 4 sig figs, 1, 2, 3, 4. So I'll just go ahead and round And there we go. That's how many grams of the iron phosphate I would need to start with in order to reach a target actual yield of 10 grams, knowing that my percent yield is always around 78%.